Okay. If my computer is uncooperative, I apologize. I have tried to record this a few times and keeps freezing up. So we're going to try again. Have an idea that might make it better. Anyways, Friday, you looked at, hopefully, chapter 22 and 23 out of your textbook. Just some basic stuff. Lots of notes I put up on Google Classroom for you. The biggest and most important part for all of that is looking at the vocabulary that you're looking at here. Now, I skipped 21 on purpose, and that's what we're looking at now, is the Hardy-Weinberg principle. So the Hardy-Weinberg principle is used statistically to quantify a gene pool using allele frequency. And the allele frequency is a comparison of the number of times a specific allele occurs within a total population, to the total number of alleles for the trait. So if you want to think back to maybe Mendelian genetics, right? We talked about big Y, meaning green. Let's try that again, yellow. And little y, meaning green in terms of our pea seeds. So if we were to look at all of the alleles in a population and found out that in a population of, and picking nice numbers here, in a population of 1,000 pea plants, we have 1,500 yellow alleles, and we have 500 green alleles. We can say, okay, well, there's a total of 500 out of 2,000 alleles that are green. And what that's, oh, come on. So 500 out of 2,000, again, that's going to be 25%, or 0.25 is the way we're going to refer to it as a decimal. So 0.25%, 0.25 are Y, and that obviously means that 1,500 out of 2,000, 0.75 are big Y. Okay, so that would be our allele frequency. Now, this does not actually tell us how many yellow or green pea plants we have. We do have a maximum, I suppose, number of yellow pea plants. Maximum we could have would be, now this is out of a total of 1,000 pea plants, right? So there's 2,000 total alleles. In terms of yellow ones, we can say, well, if they're all homozygous, that would mean that we've got 750 yellow and 250 green. But obviously, with the yellow ones, it doesn't mean that just because there's one yellow allele doesn't mean that there can't be two. In fact, we could have this set up, you could imagine a way where all of the pea plants are either homozygous yellow or heterozygous, and there's no green peas at all. But again, that's also not very likely. And this is what Hardy and Weinberg actually looked at. Now, a couple things that we should quickly take a peek at here. Number one, if there's only one exists, the frequency is 100%, and we say it's fixed. If there are two alleles that exist, what Hardy and Weinberg said is let's let the frequency of one equal P and the other equal Q. And in this case, P plus Q then has to equal 1. Usually we set P to be the dominant, Q to be the recessive. So in this case, our little example here, this 0.75, that would be P. And I don't know why. But this graphical thing is just not cooperating, so I'm going to just go back to using the text box. Let me just erase this thing. So this would mean in this situation, in this instance here, we would say that this is equal to Q, and here, this big Y is equal to P. So there's kind of two equations we have to use. First equation is this one here, P plus Q equals 1. 0.25 plus 0.75 equals 1. I can do that in my head. What Hardy and Weinberg then did is some statistical stuff, and they said, well, we can look at this and say, well, why don't we square both sides? P plus Q squared, that goes on one side, and that's going to be a polynomial that we can expand, or a binomial expansion here. 1 squared is still 1. And so what they did is they said, well, looking at this, if P plus Q equals 1, not super interesting if we take the actual numbers here, 0.75 squared plus 0.25 squared. But what we can do is if we say, well, if I square that, I get a, P plus Q squared, and you've hopefully seen this in your math classes. This becomes this bit here. Oh, settle down. P squared plus 2PQ plus Q squared equals 1. And the math, how to get to this, is something you don't have to know. There is some fairly complicated analyses that you can do to get to this. However, the important part here is that when we start looking at this, we can say, well, hey, wait a minute. P squared is the same as PP. That would be big Y, big Y. So what they're saying is statistically, if I do some of this work here and square this, I'm going to get P squared. That's going to be the frequency of the homozygous dominance. And 2PQ. So 2 times P times Q is going to give us the frequency of the heterozygous ones. And then Q times Q, or Q squared, is going to give us the frequency of the homozygous recessive. All right, so a few things that we can do with this then. Number one, looking at my example that's in the notes, then we'll look at this example over here. Example number one right in the notes here. Well, we've given a population of pea plants. Again, same that we just looked at. Big Y is yellow, big Y, little is yellow, little y is green. And now I tell you, 64 out of 500 are green. Calculate the allele frequency of big Y and little y, as well as the number that are big Y, and big Y, little y. So, have to realize, if green is given, in terms of we're looking at this is the phenotype, that's little y, which means that 64 out of 500, that is Q squared. So 64 out of 500 is Q squared. I change that to a decimal. 64 divided by 500, there I go, 0.128. Now, what can I do with this? So I'm showing some of the extra work here. How do I get from Q squared to Q? Well, if I take the square root of Q squared, I will get Q. Square root of 0.128 rounds to 0.358. Hey, that's going to be the frequency of little y in the population. Back to equation number one, big Y plus little y, or P plus Q equals 1, which means I can solve for P now. P is equal to 1 minus Q, so 1 minus what I got here, 1 minus 0.358, gives me P, which is 0.642. This is the frequency of big Y. Big Y is going to be equal to P squared. So I take that number, 0.642, and square it. That's going to give me my frequency of the homozygous dominance. right there. So 0.642 times 0.642, I get 0.412. And then I can check, look at this one here, big Y, little y, is equal to 2 times P times Q, is equal to 2 times this 0.642 that I came up with right here, and the 0.358 I came up with there, which means I've got 0.460 are going to be those ones. I can check this and say, well, I know that P squared plus 2PQ plus Q squared is equal to 1. And if I add up my Q squared, which I had right here, that's my 0.128, plus my 2PQ, that was my 0.460 right here, and my Q squared, that's this one right here. Add those up, they do equal to 1. And then I can look at this and say, well, how many organisms, right? Given that there is a population in pea plants, if I know that 64 out of 500 are green, well, how many are big Y, big Y? It's going to be 500 times my P squared, which would give me 206. Big Y, little y, 500 times 0.460, 230. So in order for Hardy-Weinberg to work, and we're going to go back and look at that other example in a minute here, we have to assume a few things. We have to assume that the population is infinitely large. Is there any population that's actually that? No. But what Hardy and Weinberg said we can do is, if it's not infinitely large, we can basically say, well, if it's pretty big, Hardy-Weinberg's going to be accurate. If it's really tiny, Hardy-Weinberg is not going to be accurate. We also have to assume that no migration occurs, right? That all of the changes to genetics in a Hardy-Weinberg population occur within that population. No mutations occur, right? So again, all changes to genetics occur within the population. No natural selection occurs, so every phenotype is equally likely to survive, and mating is random. And that's important as well, because then there's no sexual selection at work. It's not like, oh, the females all prefer males who are a certain genotype. That's actually going to influence this, and then Hardy-Weinberg doesn't work. So, back to our example we started looking at here. Oops. Couple things we need to look at. If we know that this is P and this is Q, now in this case I gave you fairly unrealistic data that how would we know this? Let's just pretend we know this, all right? In this population, assuming it is a Hardy-Weinberg population, come on, no, we are on, there we go. We know that P squared, no, let's try again. We're struggling. P squared then is going to be equal to, well, P times P, so 0.75 times 0.75. And if we look at our calculator here, this is one part of Bio 30 where we do need a calculator. And in this case, it's not that we need a horrendously good calculator, but we do need a calculator. So in this case, P times P, so we have 0.75 times 0.75 P squared. Tells me that 0.5625 or 56.25% of these organisms are going to be homozygous dominant. 2PQ, again, this is going to give me, oh, and thinking back to this, this means for our situation here, this is big Y, big Y. 2PQ, PQ, is going to be equal to 2 times 0.75 times 0.25. we end up with 0.375 or 37.5%. This, again, in our Hardy-Weinberg population is going to be a big Y, little y. And we're left then with Q squared, which is going to be my 0.25 times 0.25. It's going to be 0.0625. And this is going to be my organisms that are little y, little y. Then if I want to say, okay, well, how many actual organisms are there? Again, this was a grand total of 1,000. So this means I've got 562.5. Now, we'll talk about what that means in a minute here. 375 and 62.5. Again, I just multiplied each of those frequencies by 1,000. Oops. And if I were to add all three of these up, what we're going to see is that we end up with 1,000. All of them are now accounted for. One thing I'll just tell you here, when you get a question like this, Hardy-Weinberg frequency or equilibrium stuff, the big thing to look for is the number of recessive organisms will always give you Q squared. Q squared. We're struggling. Q shift 6 squared. There we go. And that can be worded in a few different ways. It could be worded, right, that there are, for example, 89% of a species shows a dominant trait. What I've given you there is that 89% have at least one of the dominant alleles. So that means that 89% are going to be the combination of p squared plus 2pq. But if I know that 89% show that, that means 100 minus 89, 11% do not. So if I know that 11% are not, there's my q squared. Q squared equals 0.11. Then I can find q by square rooting it. Once I know q, I come back to this. Right, p plus q equals 1. Once I know what p is, away I go. I get p squared, I get 2pq. All right. That's the Hardy-Weinberg principle kind of in a nutshell. Now, let's look at a quick example here. We can kind of work through from what I just told you. Come on. All right, so in a population of pea plants, this is like really the hardest question I can give you. Let's use a better number than the one I just had. 85% of them show the dominant trait of having round seeds. The recessive trait, recessive is wrinkled. All right. Then I could ask you, determine the allele frequencies the genotype frequencies and for each possible genotype. Those are the two main questions. I suppose I could ask you for phenotype frequencies, although that's really given in the question. So let's look at this here. If 85% show the dominant trait, what does this mean? Well, this means that big R plus big R little r is going to equal 85%, or 0.85. All right. Now, I can't just divide 0.85 by 2 to figure out how many are big R, and how many are big R, little r. But what I do know from this is that the other possibility is little r, little r. Little r is going to be equal to 1 minus 0.85, which is equal to 0.15. Once I know little r, guess what I can do? I can say, well, little r, hey, that is q squared. And I can now take the square root of 0.15. I can figure out q. So q is equal to the square root of, of 0.15. So I use my calculator. 0.15, and I take the square root of that. No, not of 5. 0.15. Take the square root of that. And that tells me that q is equal to 0.387298334620742, and so big long number. In Bio 30, we round to 3 decimal places and leave it at that. All right, once we know this, then we can immediately say, well, P is equal to 1 minus Q, which then is equal to 1 minus 0.387, and that's going to be equal to 1 minus 0.387. which is 0.613. All right. Soon as I know that, now that's my allele frequencies. Now if I want to find genotype frequencies, I can go into this and say, well, P squared, that's going to be my big R. So big R is equal to P squared, which is equal to 0.613 times 0.613. And we end up with 0.375769, so that'll round to 0.376. By the way, you should be actually running these numbers on your own calculator as well. And big R, little r, is going to be equal to 2pq, not g, which is then going to be equal to 2 times 0.37, 2 times 0.376 times 0.387. which will equal 0.291024, and so on. And then I already from up here found r squared, or q squared. So little r again is equal to q squared, which is going to be equal to 0.15. And I must have punched numbers wrong at some point. I apologize. I'm using an old calculator here. 2 times 0.613 times, and that was my problem, was the 2PQ, 0.387. There we go, that's better. I apologize, something went wrong on this one right here. This should have been 0.474. How do I know that I had that wrong? I was adding these up here and I realized they were not going to equal to 1. And so when this is my check here, is I have to take my 0.376 plus 0.474 plus 0.15. That should always give me 1, and in this case now it will. That's really the hardest type of question you can end up with Hardy-Weinberg stuff. All right. So we can do lots of math with those. You'll usually end up with a couple Hardy-Weinberg type questions on your diploma exam. But some of the more interesting stuff is, well, when does Hardy-Weinberg not apply? And it doesn't apply in small populations. You can have genetic drift will cause changes to the genetic makeup of populations. And this is just in a really small population. Random chance will cause some organisms not to pass their stuff on to their genes on to the next generations. Alright, so summarizing genetic drift, this is just random chance causing some alleles, individuals with those alleles, to disappear. And if you have a small enough population, you could lose maybe your only individual with a certain allele. And that's going to cause a change the genetic makeup of the population. In small populations, sometimes you end up with one allele becoming fixed. That means there's only one allele left, and so you don't have any more genetic variability in that one. You can take a look on page 724 in your textbook. It has a nice diagram to help with that. The idea of a founder effect is where a few individuals will leave a population and establish a new one. And that's going to mean that the new population has a very different genetic makeup than the original population. There are people groups in the world today where, a fairly closed community where they have a specific genetic problem that's really rare in other populations, but because that particular population, the founder group, that particular genetic problem was fairly common, it means that the whole population group has that as a much more common problem than the population at large. So that's the founder effect. The bottleneck effect is a dramatic reduction in population may cause the allele frequency to change very drastically. Both of those founder and bottleneck effects, usually it's not that either of those effects are meant to have the purpose of changing the allele frequencies, but they do. All right. So Hardy-Weinberg doesn't apply in small populations. It also doesn't apply when migration happens. And this is going to, in migration, the fancy genetic statistics word is gene flow, will change allele frequency. So if we have alleles moving from one population to another, we're going to get new alleles coming in. We maybe eliminate some rare ones from particular populations, that kind of thing. On the whole, migration tends to reduce differences between populations. All right, Hardy-Weinberg doesn't apply if there's mutations. Again, it can alter the gene pool. So if a mutation arises, it may alter the gene pool if it becomes somewhat common, which would usually be if it's beneficial. So, for example, bacterial resistance, or the ability for bacteria to use a new or different food source, any of those types of mutations would or could cause the gene pool to become different. usually goes hand in hand with natural selections. In this case, alleles are more likely to be passed on if they give the organism some survival advantage. So, kind of an interesting one here with sickle cell anemia. Sickle cell anemia, you would think, would just go away because people who have sickle cell anemia, it's a recessive condition. People who have that recessive condition are at a big disadvantage. The problem is, if you're a carrier and you live in a place that has malaria, you have an advantage when you're dealing with malaria. And so people who are, in this case, that 2PQ group, or if we want to think of sickle cell anemia, big S, little s, they are going to be more likely to survive, which means you get 2 people who are heterozygotes. They have a 1 in 4 chance of passing on sickle cell anemia to their kids. But of their children, anybody who has the heterozygotic advantage means that they will be less likely to get really sick with malaria. Cystic fibrosis actually works very much the same. There are certain times when having the extra mucus in the stomach can be super useful. And so if you're a heterozygote, you'll have a little bit of extra mucus, meaning that you're able to survive certain things more. Harmful mutations generally, though, are selected against. Beneficial mutations would be selected for. All right, so again, Hardy-Weinberg doesn't apply in small populations. Doesn't apply if there's migration. Doesn't apply if there's mutations. Doesn't apply in case of natural selection. And then finally, also with non-random mating. Sexual selection will determine which alleles are passed more frequently onto future generations. And one of the things to think about here is that, especially birds or something like that, attracting mates is not always good for survival, where you get plain colored birds are less conspicuous to predators, and yet brightly colored ones are more likely to mate. Sexual dimorphic traits are an example of non-random mating. Males who meet the male ideal and females who meet the female ideal are more likely to be selected. One of the reasons for that, I think, that we can see is that if a male who's brightly colored and thus more visible to predators can survive long enough to mate, it must mean that in spite of having these really non-camouflaging feathers, it must be really in having good traits in all other categories if it's able to survive in spite of having that disadvantage. All right. That really takes us to the end of Hardy-Weinberg stuff. So I'm going to stop this here. Take a listen to this. I'm also posting a fill-in-the-blanks version of these notes. You can use that along with this video and then also the other file I'm going to post. To fill that in, we can go over any questions that you have on Tuesday. Thanks.